G'day everybody. In this video today we are discussing the fundamental theorem of calculus. Obviously we talk about what the fundamental theorem of calculus is. It's very easy to state, but at the same time it's quite tricky to explain, and I'm going to do my best. In the course of that we will end up talking about definite integrals quite a lot. We'll talk about what a definite integral is. Our lesson today will be a two-part video, and in the second part we'll talk about how definite integrals relate to graphs. In particular, we'll see how we can take advantage of definite integrals to calculate exact areas. Let's have a quick discussion first about the area below a curve. I'm about to shade the area below this function. Another way of describing that area is to say the area bound by the x-axis in the curve. In a recent lesson we learned how to approximate that area. We were able to use the values of these functions, divide that area up into thin rectangular strips that were close to the curve, and use those strips to get an approximate area that we've shaded there. Even if we make those strips very, very thin, our approximations will get very good, but never will they be exact. And as we uncover the fundamental theorem of calculus, we'll see how calculus enables us to find those areas in exact terms. So this time I'm going to shade that area again. But you can see there are two functions here. We're going to shade the area below the function f of x with a small f. And as we shade that area, it's being plotted by another curve that we call f of x but with a capital F. So here you can see that the area is increasing, as is the function. It's been increasing quite quickly so far, but now it's increasing only a little bit at a time because the function is close to the x-axis, and so our capital F function is increasing but only slowly. As the gap widens between the curve and the axis, the shaded area increases much more quickly, and we can see that also occurring with the value of our capital F function. So at any point, this curve, the value of that function represents the shaded area below the parabola up until that point. So starting at x equals 0, up until any point here, that value there represents the area that we've shaded up until that point. So by doing that graph, we've ended up with another function. So when the area below a curve f of x is graphed, we get a new function, and we refer to this function as capital F of x. Now the relationship between those two functions, small f and capital F, have another side to it. If we now take the new function that we've just graphed and analyse that function for its derivative or its gradient, the slope as we go from left to right, if we were to graph the value of that gradient, the value of that slope, that value would be graphed with our original function, small f of x. So each curve tells a story about the opposite curve. This curve here with the capital F, that tells the story of the area under the original function. And the original curve, small f of x, tells the story of the gradient of capital F of x. And so that relationship is essentially what the fundamental theorem of calculus is all about. So when we actually state the theorem, it's stated mathematically exactly like this. The way we say that, an integral from a to b of a function f of x with respect to x is equal to f of b minus f of a, where this function is capital F, and the derivative of capital F leads us back to the original function f of x. So that's the concept, the fundamental theorem of calculus in a nutshell. We're going to learn to take advantage of this theorem to find the exact areas bound by any 2 points on a curve. I've started to illustrate that in this diagram. If we're interested in this orange area, and we're looking at an area between x equals a and x equals b, essentially by using the fundamental theorem of calculus, we can see it as a difference of 2 areas. In other words, we can see it as the difference of the whole area between x equals 0 and x equals b, subtract the area from x equals 0 to x equals a, we're going to end up with this orange area from x equals a to x equals b. Those values for the areas come from the values of the function capital F of x. So that point on this curve, the value of the function right there, is the entire area. This value at x equals a is equal to the area, the yellow area, from x equals 0 to x equals a. And so by finding the difference of those 2 values, we will end up with this area, the orange area, which is the one that we're after. So just to summarise up until this point, we've just covered the fundamental theorem of calculus. It's written as a definite integral, so this is what we mean by a definite integral. In a moment we're going to talk about where that comes from. And there's a relationship between small f and capital F. They tell a story for each other. And that's the second part of the theorem that explains that. The derivative of one leads us to the other. If we know what we're doing with curves, areas, also the x-axis, we'll be able to calculate exact areas. That will be the main content we'll cover in the second part of this video, second part of this lesson. Before we get there, we're going to have a talk about where this notation comes from, and it might help us understand a little better what it actually means. And we will look at one example where we calculate a definite integral. So in a recent lesson, we were approximating areas with very thin rectangular strips. Those rectangular strips had a length that was given by the value of the function when they touch the curve. That's the length of the strip. And the width of each strip is what we were calling d. In this case, we're going to refer to it as delta x, a small change in x. So each strip has this area, length times width. If we add up all of the strips, that's what we mean by this Greek letter sigma here. That's a sum symbol. So if we sum all of the thin rectangular strips, that will give us our approximation for the area. Calculus is concerned with what happens to these very thin strips as they become infinitely small. So here is our area approximated, and just a moment ago we talked about a fundamental theorem, which is an area that's exact, and you can see a lot of similarity between the way these two expressions are written. First of all, we've got our length times our width. So here we've got a length times a width, but here we're referring to the width as something that is infinitely small. Here we've got our Greek letter capital S, sigma, which means the sum, and this integral sign here is something that means to find the sum of rectangles that are infinitely small. That's a huge concept in itself. And so you can see that's why we use this notation. That's where we get this symbol from. So here's a simple definite integral. You've probably learned to calculate these in the past. I'm only doing it here as a bit of revision, but you might check the stages of working out that you could show if you were doing this with pen and paper. So in the first stage of this, let's have a look at the integral that we're calculating first of all. Here's our function, x squared minus 2. We're interested in the definite integral from a value x equals -2 up to a value x equals 3. So this is our small f. The large f is its antiderivative. So the antiderivative of x squared minus 2 is x cubed over 3 minus 2x. And you can see in here I'm now using a square bracket, and these boundary values, x equals -2 and x equals -3, are written at the corners of those square brackets. This next stage is essentially our f of b minus our f of a, where here's our a and our b. So I've substituted the b value for f of b, 3 cubed over 3 minus 2 times 3. This is our f of a, where a is equal to -2. I've kept everything in brackets, and you can see here I've just finished off the problem, being fairly careful about the way that I expand brackets, particularly when I'm dealing with values that are negative. So essentially we end up with a value that is 5/3. So we would say that the definite integral of x squared minus 2 from x equals -2 to 3 is equal to 5/3. That's the end of the first part of this lesson. If you immediately go to the second video, you can pick up where we are leaving this one off. Thanks very much.